Whether it's a combustion engine or an electric motor, it has its optimum efficiency and power range during operation. Knowing how to size a motor to match with your load, such as a propeller, turbine, or vehicle drivetrain, can either enhance the system's performance or its efficiency. In this Part 2 episode of DIY Education series, we are going to investigate how proper motor sizing and load matching can help to maximize the efficiency of your mechanical system. When a system's efficiency is enhanced, it consumes less power during operation. For a combustion engine, it consumes less fuel, while for an electric motor, it consumes less battery power. The end result is a more cost-effective operation. Before we go any further, we should first look at the definition of efficiency. Imagine we have a motor and a battery that provides power to it. When the motor is energized, the motor shaft will start to turn. The role of the motor is to convert the electrical power from the battery to the mechanical power to turn the shaft. The input power here is the electrical power, and the output power is the mechanical power. Due to the mechanical and thermal losses of the system, the output power will always be less than the input power. To quantify the output power quality of the system, we normally use the term efficiency to describe it. Efficiency is the ratio of output to input power, usually expressed in percentage. The higher the efficiency, the lower the power consumption, and the longer the system can operate if it is powered by a portable power source such as gasoline or battery. In the Part 1 episode, we have looked at how torque matching was done based on performance optimization. You can see from this chart that the required torque was selected closer to the peak power than the peak efficiency, and so the efficiency was only 46%. If we are to conduct efficiency optimization here, we will have to choose a torque value closer to the peak efficiency of 67%. While this chart represents the torque and efficiency of a motor that employs a fixed gearbox, to analyze the efficiency variation of a system that employs a multi-stage gearbox, we have to use the following chart instead. This chart shows the efficiency plots of an electric motor that uses a two-stage reduction gearbox. The black dots represent the best shifting points for the best efficiency. They are the best averages of the first and second gear plots. Do you remember we saw a plot similar to this in the Part 1 video? Yes, the plot for determining the best shifting points for the maximum performance. In this case here, we are doing it for the best efficiency instead. Now we are going to use a motor propeller system to demonstrate how efficiency can be maximized in torque matching. Say, we want to build a wind turbine generator using a propeller and a DC motor. It has to work in moderate breezy conditions where the average wind speed is about 7 meters per second. First, we should look at the torque and efficiency graph of the propeller operating at such wind speed. Identify the region near where the peak efficiency occurs. Do the same for the motor torque and efficiency graph. If the motor requires a spinning rate of 750 RPM to give out your required voltage, then on the propeller side, locate the required RPM with the corresponding torque. Next, match the RPM and torque values on the motor side. If the required torque and RPM don't match, you may have to change the size of the propeller, motor, or couple them with a gearbox in between. When the torque matching is done properly, the torque and RPM on both sides should have the same numbers. and they both should have efficiencies close to the peak values. In the case of a motor propeller system of an aircraft, we should first look at the thrust required for the aircraft to operate at steady level flight. In such condition, the lift should be equivalent to the weight, and the forward thrust should be equal to the drag so the aircraft can fly at a steady level with a constant speed. Say, if we have a small aerial vehicle which flies at around 7 meters per second at steady level flight, we should first determine how much thrust is required so each of these force pairs is balanced. If 1 Newton of thrust produced by the propeller is required to achieve such condition, then we go find the corresponding torque and RPM on the propeller thrust and torque graph. Make sure at this RPM, the efficiency stays close to the peak. Now match the torque and RPM on the motor side, just like what we have done earlier for the wind turbine. The following flowchart summarizes what we have discussed in this video. It may guide you in the decision-making process when it comes to efficiency optimization in motor load matching. Thank you for watching. If you enjoyed this video, please like it and subscribe to our channel. We will have more DIY projects coming soon.